Hello, welcome to our fourth video in our Gen Chem series. And today we're going to continue onwards with talking about the periodic table. And there's some other kind of key facts that I want to mention to you that are really important for your undergraduate classes and also, of course, the MCAT. And before we kind of look at the new stuff, I want to just, of course, start with a quick review of the previous video where we talked about the 5 major periodic trends. And I've got the same slide from last time. And we kind of saw that really they all kind of trend the same way. So they increase from left to right across the row. And they also increase as you move from the bottom of a column to the top of a column, with the one exception of atomic radius. So atomic radius we can see as the red arrow. That one has the opposite trend. Okay. And I want to just quickly go over the first two again, so effective nuclear charge and radius, because I really think they're the two most foundationally important. So let's remind ourselves what effective nuclear charge is. Effective nuclear charge, I like to say, is kind of the proton attractive force that electrons feel. And so looking at these two atoms, we've got lithium and carbon. And when we are calculating an effective nuclear charge, we typically do it for the valence electrons because, of course, it's chemistry, and the valence electrons are the ones that do all the chemistry. They do all the bonding. So those are the ones we typically care about. And so for lithium, it's got 3 protons, and those 3 protons are all going to pull equally and attract equally the outer valence electron right here. But remember, it's also got 2 inner shell electrons right here and here. And those inner shell electrons are going to repel with kind of the same force as a proton, the electron. So those inner shell electrons are pushing away our valence electron too. So if you kind of add it up, you've got 3 pulling in, 3 protons pulling in, 2 inner shell electrons pushing away. So you get 3 minus 2. 3 minus 2 equals 1 for the Z effective of lithium. And then if we did the same math for carbon, we would have 6 protons minus the same 2 inner shell electrons equals 4. So that's kind of confirming our trend that it increases across the row. And let's remember how this connects to atomic radius, or the size of the atom. So if the effective nuclear charge is going up, what we're saying is that the electrons feel a stronger attractive force, which means that they're going to get sucked inwards closer to the nucleus. So carbon really, when it's compared to lithium, is going to look something like this. So now I want to move on to the new stuff, which is I want to talk about the organization of the periodic table. So there's really 2 main things that I want you to know, which are that the periodic table is broken down into kind of 2 smaller kind of things. So it can be broken down into blocks, and it can also be broken down into groups. So let's first look at the blocks. So there are 4 blocks. The first one includes all these elements. It also includes helium. And this is the S block. Then we have the D block, which is these elements. Next, we've got the P block. And finally, we've got the F block, which is right here. Kind of those bottom 2 rows that we really just don't care about at all for medicine, or even really for undergrad courses. And the key thing here is hopefully this is reminding you of something we've already talked about. Hopefully it's reminding us of the electron configurations, right? So every element that's in the P block, for example, is in the P block because its electron configuration ends with the P orbitals. So, for example, if we were to do the electron configuration of boron, which is the very first element in the P block, you would get 1s2, 2s2, and then 2p1. So it ends with a p orbital. And so, yeah, that's kind of why they're called the SDPF blocks. Those are pretty common terms, so good to be familiar with. And then the other thing that I want to mention is that the periodic table is broken into groups. So groups are exactly the same thing as a column. So every single column is a group. And it's probably the most important feature of the periodic table, actually, because I really like to think of groups as kind of elemental families. So every column, so every group, um, shares kind of very similar characteristics. So the elements in a column tend to bond very similarly, which means they make kind of the same types of molecules. And they also tend to have similar like physical properties as well. Um, that's a really good thing to know. And there's kind of a numbering convention for this. So as you move left to right, the numbers go up. So the very first column, the very first group is 1, and the very last group is 18. Though in medicine and other fields that kind of work with biological systems, it's pretty common to just kind of skip over the D block because the D block is not super important for biology in general. I mean, there are, of course, exceptions like iron, but in general, we don't talk about it super often. So we'll skip over it and we'll number something like this 1, 2, and then skip the D block and then 3. You give the 3 to the group that starts with boron, and then 4, and go all the way to 8. So that's probably the more common thing you'll see. And if they do this kind of skipping over the D block notation, instead of it just being 3, 4, they'll call it 3A, 4A, 8A. Okay. And finally, there are 5 groups that I really want you to know in particular. It's good to know the names of these groups, and it's also good to kind of know what's special about them. So they're particularly interesting, I would say. So the very first one, I'm sure you already know, and it's the noble gases, which is the very last group. And I'm sure you know why they're called that. They're the noble gases because they're inert. They are basically, I like to think of them as being maybe a little pretentious. They like think that they're better than the other elements, and they don't really need to associate themselves with them. They're like too classy for the other elements, so they don't really make any molecules. They don't really bond with anything. And then the other 4 groups that are really important are going to be actually the 2 groups on the left and the right of the noble gases. So going from the left, the first one is going to be this group, and this is the halogens. And the halogens, being right next to the noble gases, I like to think of them as being super jealous. They're super envious of kind of their noble status, and they really look up to them. They would love to be them. And um, what they would love to do in particular is to have the same electron configuration. So I should have probably mentioned this when I mentioned noble gases, but what makes the noble gases so special and the reason they're not reactive chemically is the fact that they have a complete electron shell. So all of their electron shells are totally full. So like neon, for example, um, its electron configuration is 1s2, 2s2, 2p6. And remember, a shell is all the orbitals with kind of the same principal number. So the 1s2, all the 1 orbitals are completely full, and then the 2 orbitals, so 2s2 and 2p6, those are also completely full. So the noble gases have completely full shells, which means that they're really stable. That's kind of the most stable configuration for an atom. Therefore, the halogens would love to have the same electron configuration, which means they would love to gain 1 electron. So halogens, they want 1 electron really badly because that would make them have the same electron configuration as noble gas. And then the next group to the left of the halogens is the Chalcogens. Hope I'm saying that right. Chalcogens, and they kind of are similar to the halogens in that they're pretty close to noble gases, and they really want 2 electrons to have the same configuration. And then if we look to the right of the noble gases, so you kind of have to wrap around the periodic table. For example, looking at this group, this is our alkali metals. And then the next group is the alkali earth metals. And if you're wondering if the names of these are actually important, yes, they are. They actually came up on my real MCAT. I was pretty surprised by that, but I had two questions on this. So I don't know. Maybe I'm overvaluing how important this is, but it's definitely fair game. So I would just kind of commit these to memory, and it does come up fairly often. Anyway, the alkali metals, they actually want to do the opposite. So if lithium, for example, which has electron configuration 1s2, 2s1, if it somehow just lost or gave away its 2s1 electron, it would be the same thing as helium. It would have the same electron configuration as a noble gas. So the alkali metals really, really want to give away one electron, and the alkali earth metals want to give away two. All right, that wraps up about everything I want to talk about with the periodic table today. Segueing into the next topic, which is going to be intermolecular bonding and polarity, I'm going to leave you with two questions to kind of think about and maybe answer for yourself that I'll go over in that next video. So I've written them out here, and the first one is, what do groups 3A and 5A want to do with their electrons? Also, what is strange about group 4A? And then finally, do any of the groups seem like ideal matches for each other? Okay, I want you to think about that, come up with a good answer, and then we'll go over it. So thank you for watching this video, and see you in the next one.